All right, so we're going to round up this week um, by three very fundamental laws, Planck's law, Kirchhoff's law, and Stefan Boltzmann's law. And we're going to be using some concept we learned in terms of the radiative transfer. But these are three very fundamental laws which are going to be very important and useful. So it's good to understand when they're applicable and then remember them. Okay. Now, the first one's Planck's law. Let me get rid of this somehow. I can't get rid of it for some reason. Anyhow, so the first one is Planck's law. It went by itself. Okay, so the first one is Planck's law, and Planck's law basically gives you the specific intensity of a black body in thermal equilibrium. So those two terms are very important. The term black body, which is the first condition, and thermal equilibrium, which is the other condition. So what's a black body? A black body is a body which absorbs all the radiation that is incident on it. Okay, that's what a black body is. So you can think of it as a medium whose optical depth is always far, far larger than 1. So everything is absorbed, nothing comes out of it. So if you shine any light on a black body, nothing goes through. That's what it means. So, and that should apply at all frequencies. Okay, so you can think of it as a medium which has a very high optical depth at all frequencies. That's a black body. The second condition is thermal equilibrium, and that means that there's no net energy input or output into the body which is emitting, into the black body in this case. And that's what you call a body in thermal equilibrium. It's not heating up or cooling down, and it has had enough time to assume a natural state. And by natural state, I mean that the velocity distribution of all the kinetic motions of particles have assumed a relaxed state, and so in terms of a statistical ensemble, they are not changing. Okay, so their distribution function is not changing. So that's what a body in thermal equilibrium is. And so if these two conditions are satisfied, then the specific intensity is given by the Planck law, and that's the law here. So this is I basically for a black body. So this has units of ergs per second, per hertz per square centimeter, per steradian. So this is specific intensity. And I've written out a sub nu here, a subscript, because a lot of times you will encounter the Planck law expressed in wavelength units. So instead of per hertz, it's going to be per micron wavelength or something. But anyway, this is the standard way to do it. And so if you're doing it in the standard way, you would say B of sub nu to say that this is per hertz. If you see B of lambda there, then it's per unit wavelength. That's not usually how it's done. So this is more, you're more likely to encounter this. And notice a pretty remarkable property here. There's only one argument, temperature, and nothing else. And that's why this law is so fundamental, because the right-hand side, the only parameter here is the temperature. Once you specify the temperature, this is a fully specified curve as a function of frequency, okay? So H is Planck's constant, so that's a constant, C is the speed of light. And that is why this law is so fundamental, because it does not matter what the body is made of. It doesn't matter what its internal constitution is. None of this matters. As long as it's a black body and in thermal equilibrium, its specific intensity will always have only this form, and it will only depend on the temperature of the body, not its other material properties. And so we're going to derive Planck's law in class, but it's good to know the domain in which it is applicable and why it is of such fundamental importance, because it is a fundamental property of matter and radiation itself, because none of this depends on the actual constitution of matter or what the matter is made of and how it is emitting. As long as it's a black body and it's in thermal equilibrium, this is the specific intensity of the object. It's quite often that you would encounter what is called the Rayleigh-Jeans limit of the Planck function. So this happens where the frequency is very small, and by small, I mean h nu is small compared to kT. So this factor can be Taylor expanded out. And then this is just the Planck law in the limit where h nu is far, far less than kt. And that's called the Rayleigh-Jeans limit. But essentially, the fundamental law is this. This is just a limit which is very often useful. Okay, so the next law I want to talk about is Kirchhoff's law. So Kirchhoff's law is a relationship between the absorption and the emission coefficient, which we have been talking about. But here there's only one condition. Okay, so for Kirchhoff's law to apply, all you need is a body in thermal equilibrium. It does not have to be a black body. Okay, so you remember Planck's law had both conditions. There's only one condition on Kirchhoff's law. It has to be in thermal equilibrium. And the law says that the ratio of the emission and the absorption coefficient is the Planck function. This is again a very fundamental relationship because it tells two things. One is the obvious thing which this equation is telling you, which I've written here, is that every emission mechanism has an associated absorption mechanism. And so if there is some emission mechanism or an emission process, and then you can go through the microphysics of it, calculate the emissivity, this law is basically telling you that you need to also have an absorption by the same process. So if an electron is emitting photons by some process, by the same process, it should also be absorbing the photons. And so you can't have just emission in a medium. Emission always comes with absorption. Absorption always comes with emission. So that's the fundamental thing that Kirchhoff's law is alluding to here. And the second thing is not just that emission and absorption are related, they're really should be thought of as the same mechanism. It's also that their coefficients, the ratio of it, is this universal function. Again, this does not depend on the material properties of the body. So it doesn't matter what the mechanism of emission is, it doesn't matter what the properties of the body are, as long as the emitting medium is in thermal equilibrium, these two coefficients are tied to the Planck function. And so that's why, again, this law is of fundamental importance. It's kind of nice to see that Kirchhoff's law will reduce to Planck's law for black bodies. So remember, here we only applied the first constraint that the body has to be in thermal equilibrium. We said nothing about it being a black body. So now let's say that it is a black body and see what happens. So a black body, again, is one whose optical depth is very high because any radiation entering the body doesn't leave, which means that it's completely absorbed in the body. So its optical depth is extremely high. And then we can go back to our equation of radiative transfer and then see what the solution to the equation was for tau far, far greater than 1. So we found that if the optical depth is very high, it's an optically thick medium, then you basically get the result that the specific intensity is the source function, right? So that's what we showed in the limiting case of high optical depth. Now the source function is that ratio of the emission to the absorption coefficient, and that by Kirchhoff's law is equal to the Planck function. So what is this saying? If you have an object in thermal equilibrium and it is a black body, your specific intensity is the Planck function, and that is basically Planck's law. So Kirchhoff's law reduces to Planck's law for black bodies. All right, so the last one is Stefan Boltzmann's law. I tend to not think about this as a fundamental law in at least the way this material is presented, because you can always derive this law from the Planck function. Anyway, so the Stefan Boltzmann's law gives the power emitted by a black body per unit area. So this is energy per unit time per unit area. And you already know what a black body does from the Planck function, but of course the Planck function gives you specific intensity. So it's energy per unit area, energy emitted per unit time per unit area. So that's basically what we are after, but the Planck, the specific intensity also has per unit solid angle and per unit frequency, right? So you just have to integrate over solid angles and you want to integrate over frequencies. So it's literally as simple as taking the Planck function over here and integrating over solid angles and frequency. And so I've done that in the notes. So it's just a simple mathematical exercise. So I'm not going to repeat it here. You should refer to it. You can read about it in the notes. But the result you end up with there is that the power per unit area of the black body, so I'm calling it P here, is some constant, and this is just a constant. That's called the Stefan Boltzmann's constant times temperature to the power 4. So it's a very high power of temperature, and this has all kinds of consequences. This basically tells you that it's very hard to maintain a black body at high temperatures, because the more, as you increase temperature, the amount of power it's going to radiate and cool down, tend to cool down, goes up as the fourth power, so which is a very high power of temperature. But it's also handy, once you know the constant here, it's a handy way to calculate what's the total energy emitted by a black body. So yeah, so those are the three laws: the Planck's law, the Kirchhoff's law, and Stefan Boltzmann's law. In particular, Planck's law is of fundamental importance, which I'll derive because it says something fundamental about radiation and matter itself and their interaction. And Kirchhoff's law is going to be very important in the course because in many cases, when we study emission mechanisms, it's very easy to derive the emission coefficient, but it's a kind of difficult in terms of physical intuition to derive the absorption coefficient. And so you just have to do one. For a thermal body, you can always get the absorption coefficient from Kirchhoff's law. I must say that Kirchhoff's law can be derived. We'll come to it later in the course when we do synchrotron emission. I won't really derive the law, but you'll see how you can actually derive it based on, you could argue, a more fundamental concept, which is Einstein coefficients and relationship between absorption and emission. So you can actually use that and derive Kirchhoff's law. We won't do it formally, but we'll kind of follow that formalism when we do synchrotron emission. So for now, just take the law as granted, and it'll be clear to you how the derivation progresses when we do synchrotron emission.